Hello everyone, I am Subham from IT Bhubaneswar and in today's lecture I will discuss about the E2 elimination reaction. Okay, let's start. First, in E2 elimination, we have to use a strong base. It can be bulky, it can be non-bulky, and formation of double bond occur in E2 elimination. Let's see the reaction of E2. That is, if there is a one CX halogen bond and one is hydrogen, then when we use base with heat, then alkene formation occur, this type of phenomenon. Okay, now let's see the mechanism. That is like this: if there is a halogen and X and here is hydrogen, when we use a base which can be like tertiary butyl oxide, that is bulky base. So this base will abstract this proton, and at the same time when this bond is break, this CX bond is also break. Okay, and the alkene formation occur, and this transition state will be like this. Okay, both CH bond breaking and CX bond breaking occur at the same time. So so now let's come to the kinetics. Now, as you know, it is one step mechanism, concentrated mechanism. So the reactant and the we can say base both take part in the kinetics of the reaction. That's why we can say rate is directly proportional to the breaking of RX bond. Okay, sorry, the concentration of substrate plus into the concentration of reagent. That is a base we used here, tertiary butyl oxide. Okay, so now we can say from here the order of the reaction is 2. You can see it is one step reaction, but because of the role of base and substrate, it is of second order. That's why we say in this reaction E2 elimination reaction. Okay, now let's come to the reduced selectivity. Reduced selectivity, like when it will give ZCF product or ZZF, and when it will give Hofmann product. Let's see. Now, it if there is a bulkier base, if there is a bulkier base, or bulkier base, or we can say bed leaving group, then we always get Hofmann product. Okay, we always get Hofmann product. Let's see how. And if there is a another condition, like both the good living group and non-bulky base present, then we will get ZZF product. And ZZF product means more substituted alkene as compared to less substituted alkene. Okay, and if there is a Hofmann, we have to write it like this. Okay, so here you can see it is less substituted because 1 2 3 4 5 6 7 alpha hydrogen, 1 2 3 4 5 6 7 8 9 10 11 alpha hydrogen. So it is more substituted, we can say more number of alpha hydrogen. That's why it is ZCF or ZCF product, and it is Hofmann product because it have less number of alpha hydrogen as compared to this alkene. But the structure we can say both species have same. So now let's see, like if there is a substrate like this, CH3 CH2 CH2, here is halogen which is a leaving group, and here is CH3. So now if the halogen is like we can say chlorine, bromine, OTS, and OMS. These all are good living group. So we can say if there is a good living group plus a non-bulkier base. Non-bulkier base means the weak nucleophile and strong base. Non-bulky, non-bulk, sorry, non-bulkier base means strong nucleophile and also strong base. That's example is NaOET, KOH. These are less bulkier base, okay, and less bulkier base, and so they will act as a strong nucleophile. So in this condition, we will get Sedgwick product, okay. And if there is a, like, if the halogen we use as a living group is equal to fluorine and the tertiary amine, it is also substituted. That's why it makes 4 bond and I put positive charge on it. And if there is a NH2, that is NH2 then or if there is a bulkier base will be like tertiary butyl hydroxide by tertiary butyl potassium, and why? Because it is like this. Now you can see it is a bulkier base. So we can say if there is a halogen F or and the bad living group, that this type of bad living group, or bulkier base, then the Hofmann product will be the major product, okay. If only one condition is satisfied from here, then we will get Hofmann product, okay. Let's see the stereochemistry of the reaction. Stereochemistry, come to let's understand it with, take an example. Like if there is a bromine, okay, it is JAM 2010 question, and if there is a deuterium, and here is hydrogen, and here is CH3, and here is hydrogen. So now when we use tertiary butyl oxide, okay, when we use tertiary butyl oxide, here you have two choice. This proton can eliminate, this proton can eliminate, or we can say three choice. This proton can also eliminate. So now which proton you have to eliminate? That is in E2 elimination, always anti-periplanar proton will abstract. Anti-periplanar, which means the neighbor carbon just next to the CX bond have different plane as CX bond. As you can see here, the CX bond is above the plane, and here the deuterium is in like below the plane. So that's why this base will extract this proton, okay, and this bond will break like this, and this CX bond will break, and the deuterium will be abstracted, and the formation of alkene occur. And here is hydrogen, and here is CH3. So from stereochemistry you can say always anti-periplanar proton will be abstracted, okay. So this type of reaction is E2 elimination reaction. And the I have to give some example of bulkier base. That will be bulkier base NaOCH3 thrice KO tertiary butyl, NaO tertiary butyl, and one is also this Ag2 H2 and heat, okay. So this type of base is present, then Hofmann product we will get, okay. So you can see if only one condition is satisfied, bad living group or we can say bulkier base, then Hofmann product. And if it is important, and if there is a good living group plus non-bulkier base, both conditions have to satisfy, then we will get Sedgwick product, okay. So this is the overall conclusion of E2 elimination mechanism, reaction kinetics, residual activity, and stereochemistry. If you have any doubt, you can drop it in comment section, okay. Thank you.